Hello everyone, so in this lecture video I will be doing an introductory lesson on the gas laws, specifically on the kinetic molecular theory, which is the slide in front of you, as well as some basic conversions between different, in this case, units of temperature and pressure, okay? So in your PowerPoint slides, there were like a bunch of like, in this case, tenets, or in this case, rules for the kinetic molecular theory. But the whole basis of the kinetic molecular theory actually are two things. A, that gas particles are very, very, very far away from each other. So the molecules in gas particles are quite vast distances between each other. And so because of this phenomenon, because of this vast distances between these gas particles, they have high kinetic energy, which is proportional to their temperatures of the environment that they're in, and that temperature has to be in Kelvin. That's a very, very important behavior. And the other thing is because they're so far away from each other, obviously there are no intermolecular forces, and we're talking about attractive or repulsive forces in play. So there's no ion dipole, 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 none of those interactions that you have previously learned in intermolecular forces. And as we already figured out before, the reason why the three states of matter actually occur is because, again, because of the strength of intermolecular forces between particles, which is proportional in this case to the distances, or in this case, inversely proportional to the distances between them, which means to say that the stronger the intermolecular force between two particles, right, the closer they are together, right? So there's a few, I guess there's a few rules here. So what that means to say is gas particles do not attract or repel each other. And what that means to say is when they collide, there is no energy transfer. In this case, there is actually no energy reaction. There's actually no chemical reaction that occurs when two molecules together. An example would be two chloride, in this case, two diatomic chlorine molecules, which is in a gas phase. That's Cl2 actually. If they collide, they will not react with each other. They will remain to be Cl2. Okay, so that's a very, very important thing. And so because of this, there are actually a lot of relationships that actually is in play when it comes to the kinetic molecular theory and what we call as ideal gas behaviors. What does this mean? Well, obviously, the more particles you have, okay, that means to say the more moles of gas you have is the more particles you have. Recall Avogadro's number, which means to say is there's going to be more frequent collisions with each other and obviously with the walls of the container that they're in. And obviously, if the more particles you have, the greater the pressure that is actually exerted in the in the walls of a rigid container, right? If the walls of the container that the gas particles are in, however, are flexible, what happens is the actual volume expands, right? So the more gas particles you put in, obviously there is going to be an expansion of a non-rigid container, like a balloon, right? The more you put, the more gas particles you put in, the bigger the balloon gets. Okay, uh, and obviously the pressure and volume is also in this case is again very, very much related to temperature, as you can see here. If you increase the temperature, that means to say that the speed, the kinetic energy of gas particles increases. Okay, and what that means to say is again the more frequent they will collide with the walls of the container. If the walls of the container is rigid, that means to say the pressure increases. Just remember, like if you over pressurize your tire, what happens to the tire? It blows up, right? And that is actually a manifestation of pressure in the system. Okay. Obviously, before your tire blows up, sometimes there's actually an increase in volume, and again, that is in this case proportional to the temperature in Kelvin. Right. Now, there are two conditions in which ideal gases, okay, and the kinetic molecular theory uh, no longer applies to a large degree, and that is these two conditions. If you have high pressures or extremely small volumes and extremely low temperatures. What does that mean? Obviously, if you cool down particles, what happens is their kinetic energy decreases. And if their kinetic energy decreases, right, they start to interact with each other, right? They no longer bounce off each other. What happens is they aggregate close to each other and they become a solid, right? Extremely low temperatures. So therefore, the spaces between them is no longer vast, and therefore they no longer in this case meet the kinetic molecular theory tenets. Okay? The other thing is obviously is high pressure. What does that mean? If you have extremely high pressure in a container, if I make the container in which the gas particles are in very, very small, which is shown here, What happens then is the gas particles now are going to be very, very close to each other. And what happens when particles are very, very close to each other? Intermolecular forces occur. Okay, so those are a couple of exceptions, the couple of conditions in which they are no longer acting as ideal gases, and in this case, the rules of the kinetic molecular theory about inelastic collisions no longer apply. Okay, so that's that. So basic conversions. So this is actually in your conversion factors, which is actually in page 7 of your exam reference sheet. And this is a very, very straightforward dimensional analysis. So what we have here is we're trying to convert 20 degrees C to Kelvin. So in order for us to set this up, you just need to look at the formula that's actually in the temperature, and you can see K, according to the page 7, is just the temperature in Celsius plus 273. So 20 plus 273 equals 293 Kelvin. Note the ideal, in this case, the significant digits rule. If you look up on top, there are 3 significant figures in the given number. Therefore, your answer has to be in 3 significant figures. Okay. Similarly, if we convert 100 degrees Fahrenheit to Celsius, that formula is actually in this case is in Fahrenheit minus 32 divided by 1.8, which is again in page 7. So again, you will take 100 minus 32 divided by 1.8. That gives you 37.78 degrees Celsius. Why do I have 4 numbers here? Because the given number has 4 significant digits. Okay. So these are very, very straightforward conversions. Okay. 38 Fahrenheit. There's a little bit more of a wrinkle to this thing. So we need to convert 38 degrees Fahrenheit to Kelvin. Now, you can do this 2 different ways. What you can do is you can actually convert Fahrenheit first into Celsius, and then at the end, obviously convert that Celsius into Kelvin, which is a 2-step process. Or what you can do is you basically relate this to relationships. Right? First of all, we know that Kelvin is the temperature in Celsius plus 273. And we also know that Celsius is Fahrenheit minus 32 divided by 1.8. So what we can actually do in this case is we can take this Celsius formula then, this is from algebra, and we can actually plug it in and replace the C by this whole mess. As you can see here. So as you can see here, all this C here, okay, this Celsius has been replaced by this whole formula. So now we have Fahrenheit minus 30 divided by 1.8 plus 273. Okay, so if we do that, 38 minus 32 divided by 1.8 plus 273, we get 276 Kelvin. Okay, I kind of broke some rules of significant digits there because there's only 2. This should have been 280K. All right, so that was my mistake. All right. Similarly, if we convert 500.0 Kelvin to Fahrenheit, again, we can do it. We can go from Kelvin to Celsius, Celsius to Fahrenheit, or again, we need to remember that there's a formula for Fahrenheit, right? A formula for Kelvin. Now, in this case, the formula for Kelvin does not actually show you C. So what you can have to do is subtract 270 to both sides, and what happens is this formula now gets transformed to K minus 273. Now we have a formula for C, and what we're just going to do with this is we're just going to plug it in right where C is, like so. Right, so this C has now been replaced by K minus 273, and if we do that, 500 minus 270 plus 32 times 1.8, all of that stuff. Actually, you need to do this inside the parentheses first. 500 minus 273 times 1.8 plus 32, we get 441 degrees Fahrenheit. What am I doing here, guys? Because I'm just breaking all kinds of rules of significant figures here. This should have been, we need to have our answer in 4 significant figures because this is in 4 significant figures. Okay, so that is temperature conversions. So again, it's in page 7 of your exam reference sheet, right? Pressure conversions is similar. Okay, so this, however, appears in page 9 of your exam reference sheet. And all you have to do is you go all the way down in the middle portion of page 9. There's going to be this ideal gas equation, and right underneath it should be a relationship between ATM, millimeters of mercury, which is mmHg, torrs, which is the same as mmHg, psi, and pascals. Okay, so dimensional analysis time. So we try to convert 50 psi into pascals. So in dimensional analysis, the unit that's given to us, which is 50.0 psi, pound per square inch, has to be the same unit underneath. The 14.7 psi comes from page 9 again, and the 101325 pascals is from the same page. So we cancel the psi, so the psi cancel in this case, right? And we're actually just left with pascals. And again, in this time, I'm actually following the rules of significant digits. So we actually have 3 significant digits, and the unit is 345,000 pascals. Okay. Similarly, if we try to convert pascals into kilopascals, just remember that in this case, you just have to remember your metric system prefixes. There's always 1,000, okay, pascals in a kilopascal, so we actually do the same thing. Eliminate the pascals, and what we have is 0.0025 kilopascals. 2 significant figures, 2 significant figures. Just think of it this way. This is just kind of like converting into from meters to kilometers, in this case, kilometers, right? So just remember that. Similarly, if we're trying to convert 800.0 millimeters of mercury to ATM, or it could be 800.0 torrs to ATM, again, we go into that page 9 again, and based on that relationship, the ratio that relates ATM and millimeters of mercury is 1 ATM has 760 millimeters of mercury, cancel units, 4 significant digits, 1.053 ATMs, right? Basically, again, as I mentioned before, it's just significant figures. Converting 2.2 ATM to PSI, again, sorry about this this little thing here. We are gonna ATM is on the bottom again. They cancel each other out, and we have PSIs, pound per square inch. Okay. Last problem. Converting 320,000. Oof, I'm missing a zero here. Pascals to millimeters of mercury. Obviously, again, the pascals is underneath in the relationship. And again, these two numbers are always from the page 9, just like here, here, here is not. Obviously, it's from your metric system. And here, these are all in page 9. Okay. And again, cancel units, and you're left with 24,000 millimeters of mercury. 2 significant figures. 2 significant figures. Right? Lastly, I'm just going to talk to you guys about the gas laws. Okay, so there's many gas laws. There's Boyle's law, okay, Charles' law, Raoult's law, all of this stuff. But the main thing about this laws is knowing what the relationships are. Okay, and I am probably going to stop this lecture video, and I'm going to restart this lecture video again in a much more extensive, in this case, covering of what the ideal gas equation actually means. Right? So make sure that you watch the upcoming next video.